Hello everyone, we will be talking about mirrors and lenses in this video. Now you're typically going to see this in some sort of Physics 2 course. It's pretty simple. You've all seen mirrors and lenses in your life. Maybe you use some of them. I know with me, with my glasses here, I have a set of lenses that I use. Anywho, we're going to be going over the physics of it. This might be a very involved lecture. There's quite a few formulas and general things to get over. We'll start with mirrors and go on to lenses. So let's begin. So let's understand the most simple of mirrors first, because first we're going to talk about mirrors. The first one we have is a plane mirror. And this one is quite simple. You've seen plane mirrors before. If you get ready in the morning, you typically will see these. And it's quite simple in its form. And it's what the name suggests. It's a plane mirror. So it's that of a plane. So let's talk about the first law you're going to learn. And this is a fundamental law that we'll be using a lot in our explanation of mirrors. It's going to help us understand convex and concave mirrors respectively. And it's this idea of the law of reflection. And it says that if I have an incident ray of light that's going to hit the mirror, the reflected ray will share the same angle to a normal. Now, that might seem a little bit scary of terminology, normals and all that, and angles maybe, but it's quite simple. A normal to a surface, a normal is like perpendicular but for 3D. So imagine the word perpendicular, which we refer to 2D, where something, two lines or two, any straight things, rays, make a 90-degree angle. A normal is just a 3D terminology for that, but you're going to see it here in these 2D representations, and that's the idea of a normal. So I'll write that terminology down for your notes. Normal equals perpendicular. You'll see the idea of a normal come up in a lot of engineering contexts, specifically in Calculus 3 when you're talking about let's say gradients, right? For example, those give normals to surfaces. So it's stuff you'll see if you're an engineer. If you're just a general science major, maybe not so much. But a normal is the perpendicular between these two rays. So this is the incident ray. We call any ray that's striking a mirror incident. And then the reflected ray, of course, is the ray that is reflecting off of that mirror. Now we have the incident ray coming in at some angle, and we're going to call this theta I, the incident angle. And the reflected angle is theta R. And like I said, the law of reflection says that theta I equals theta R. So the law of reflection is a very fundamental relationship for any plane mirror or any ray of light hitting a surface to the normal to that surface, that instantaneous plane, that normal to it, it's going to reflect about that and give you the same angle about that normal. So theta I equals theta R. Okay, and this is going to help us understand some other mirrors we're going to look at, such as concave and convex mirrors. Okay, now that we have that out of the way, I want to talk about ray diagrams or ray tracing diagrams. They're very important. They're going to help you understand the image that you see. Now, an image in a mirror is, when you look in a mirror, you see something. That is the image that you see. And in a plane mirror, it turns out that you get these things called virtual upright but inverted images. Now, that's probably the only mirror you've seen. Maybe in a convenience store, you might see other types of mirrors, for example, or in other applications, like maybe in your car. But plane mirrors are the ones that you're most comfortable with. And to understand how you're getting the image, you have to draw a ray tracing diagram. Now, you can do mathematics, of course, but for this lecture, we're going to look at such diagrams. So let's take a plane mirror like this. And let's say here's the mirror. So here's the ground, here's the mirror. And let's say I have a person standing right here. Okay, what is he gonna see? Well, understand that people and everything in this world is emitting photons to you. So, for example, my hair, if I looked in a mirror, photons from my hair are gonna shoot towards the mirror and get reflected back to me. And that's what mirrors are doing. They're reflecting light coming off of you back into your eyeball. So let's show that with a ray tracing diagram. So how you do it is you draw at least two rays from the mirror. You follow the law of reflection and you see where the lines or the rays are going to converge to. We'll see it's not so cut and dry later, but this is applicable to plane mirrors. So let's look at this. We have Bobby here, our nice test subject. Let's say we want to know where the top of his head is going to be. Well, we know that a ray might come straight across, and we know since it's a plane mirror, the normal is that trajectory of that ray. So when it hits the mirror, it's going to bounce right back. Okay, let's now consider a ray that might hit maybe here. So we have a ray that hits about halfway in the mirror. Well, we know if it's going halfway, it's going to get reflected to the floor to go the full way. Now you might be asking yourself, what image are we seeing? And for an image to be seen, you have to have light rays converging. That's what we call a real image. So if light rays converge to a point, we're going to see that that's a real image. However, if it seems that behind the axes or behind this mirror, as we'll see, if you can extrapolate backwards behind the mirrors or where they would have been going, you can see what's called a virtual image. And we'll talk about the distinctions later, but it's going to be important for this plane mirror description because notice the light rays are not converging. So light ray 1, when it's reflected, goes this way, and this ray is going this way, and you can notice that the rays are never going to converge no matter how far they go. And this is where we have to extrapolate backwards. So we extrapolate behind the mirror to follow the trajectory of the reflected ray, and we see that, and specifically going backwards on this one and backwards on that one, we can see that we get a point here of convergency. So it appears that they converged behind the mirror. Okay, so, and you only need two, and you can do this with as many points as you want, but what you'll see is that you get Bobby back on the other side. When you add up all those little points from all those points on Bobby, making those ray diagrams, you'll get Bobby back, but flipped around, of course, as we're familiar with in our life. Okay, that's a very simple ray tracing diagram. We'll see they get a little more complex when we talk about convex or concave mirrors specifically, but hopefully this was helpful to see just the basic fundamental ideas of ray tracing diagrams and seeing what an image might look like. We'll talk about real and virtual in a minute. But notice, it's the law of reflection. Use that to understand where your image is. Okay. Let's talk about another formula here that will be important. So, or actually, before I show you that formula, let's talk about these types of mirrors that we might see. Specifically concave or convex. You can have a convex mirror. Oh, my marker's dead. That's no good. 1 second here. I might not have another black marker. Oh no. Oh yes, I do. Okay. We can have nice and bright too. We can have a convex mirror, and a convex mirror is convexing, so it's bulging out. And it might look something like this. You might see this in a convenience store to help see further about. We'll see about that in a little bit. So that's a convex mirror. But we also have a concave mirror, and it's just the opposite of a convex. So where we're bulging, we're caving. And these are two mirrors that you'll see, and they give rise to different images. Remember the plane mirror we saw, image where we got roughly the same size back, and in fact we'll always get the right side back. But in these mirrors we actually get something a little different, as we'll see. But we have to understand the idea of a principal axis ray. Kind of an interesting term, but it's a way that we can describe these mirrors and where their rays are going to go by talking about rays. Why did I pick that up again? Rays that are going straight onto the mirror. So what this looks like, in the example of a concave mirror, we're going to have these rays that are moving in the same direction straight towards the concave mirror. And we need to define a very important point of these mirrors called the focal point. So here is our F focal point. So let's define what a focal point is. A focal point is a point where principal axis rays will be reflected through. So sorry, the notes are going to get a little interesting here, but a focal point is a point where all your principal axis rays are going to be reflected through. So let's consider a concave mirror. It turns out that the focal point is on this side of the side where we see that concavity and our rays are approaching. And what happens is that the reflected rays will go through this focal point. Okay, so this one just, this middle one here is just going to get reflected back, and this one this way. Okay, and that's going to be important to understand when we talk about ray tracing diagrams, of course. And it's all this big idea of the focal point, so please keep that in mind. A convex mirror is actually the opposite. We have the focal point beyond the mirror. And when we have our principal axis rays, they instead extrapolate backwards, because this one is going to get reflected because it's hitting right the middle. It gets extrapolated back, and then this principal axis ray will go something like this. So all these rays, they're approaching on the principal axis, or the one that's straight on, and they're getting reflected, but it looks like they all originate from the focal point, from the surface of their reflection. And they'll all do that. So that's the idea of the focal point. It's a very important idea. A cool example is in a concave mirror, you can have a solar cooker. If you have something like the sun, which is so far away, the only rays hitting it basically are straight on, and it's going to funnel light onto this focal point, which in this case, if it's a solar cooker, it's going to be your food. So kind of an interesting thing there. But the big takeaways conceptually is the focal point, what a convex mirror looks like with its principal rays, and what a concave mirror looks like with its principal rays. Okay, let's erase this here. Okay, now let's discuss a very important formula. It's called the thin lens equation, or the mirror's equation, and it follows something like this. So it says that your object distance d sub naught, so wherever your object is, added to 1 over the image of your image is equal to 1 over f. You might also see this in your class as 1 over p plus 1 over q equals 1 over f. So either way you see it, I'm going to go with this. I think it's just a little more intuitive that way. But your object, 1 over your object's distance plus 1 over your image distance equals 1 over the focal point. So it's a very fundamental law that you'll see. And that's called the thin lens equation. We also have another one, and it's very simple. 2 times your focal point equals your radius of curvature. Now, your radius of curvature, let's say for example I have a concave mirror. and let's say this is my focal distance, the radius of curvature is two times that. So this is r, and what this means is this is where the radius of your circle, if your mirror could extend as a circle, would be. So it's equal to this distance, which is the radius of your circle, thus the radius of curvature of the mirror. If your radius of curvature is larger, well then you have less of a concavity to your mirror, of course, so maybe something like that. Your radius of curvature will go all the way out there. So another important idea, it's important point that we must discuss. Okay, now let's talk about concave, convex mirrors and the images they make. So let's start with a concave mirror. Let's draw a ray tracing diagram for one of these. Let's say it looks something like this, okay? And here is your focal point F. And let's say you have an object before the focal point, so right here, okay? So pretty simple. Let's try and understand what kind of image we'll get in this case. And I recommend every time you get a problem, draw your ray tracing diagram. It will help you see be a little bit beyond the math, although if you're crunched for time, maybe not. So let's assume that this arrow is our object. So this is d naught. Whatever distance from the center of the mirror, this would be d naught. And here's our focal point F. Now, what's going to happen is you're going to see a ray maybe going on the principal axis. We know that it's going to go through the focal point then. Okay, pretty simple. And now let's imagine one that goes to the middle. Now, this ray, we know that when it hits, it's going to undergo the law of reflection, because if this is the middle point, we're going from this kind of concavity to a reversal of it. Kind of like if you've ever taken calculus, when you hit the very tip of the slope, the derivative sign changes. It's the same thing. And it's completely flat here, much like a plane mirror. So then we can say, okay, this one might go something like this. And in this case, I didn't draw my rays quite the best, but I just want to make sure that you guys can see this. Hold on. I'm going to actually kind of exaggerate this just to make it a little bit easier. Okay, so let's say the lines or the rays converge right at this point. And let's draw an arrow there. It turns out when you have the rays converging to a single point, that's going to make an image. Now, an important distinction I would like to make, if rays actually converge so if the rays are actually converging, this is going to give rise to a real image for lenses and mirrors. So if the rays are actually converging like they are here, that's a real image. If the rays seem to converge behind, that's a virtual image. So we'll see examples of both, but just keep this in mind. It's a very conceptual thing. If the rays are converging, it's real. If they seem to converge, it's virtual. And if you notice, the rays are actually converging here, so you're getting a real image. But notice that the image is upside down. So if you looked in this mirror, right, you might assume like the image might look something like this. It's going to look like an enlarged version of this when you're looking at it, and it's going to be upside down looking to you. So we can actually even define specifically how much it's enlarged and if it's inverted or not. And that's another formula that we can look at. And that says that M, the magnification, equals negative the image distance over the object distance. And there's a negative sign. Notice that df and d naught will have the same sign. In this case, if you're on the same side as your, on the left side, you're positive. All right, so positive, positive, you have a negative. That leads you to believe that if your value is negative, you have an inverted image. However, if this image was now on this side, it would be an upright image. We would see it something like this. So just something to keep in mind here. It's a very important formula. And let's say like you forget a ray diagram. Well, then you can go to this formula and see what kind of inversion you might have. And again, if you have positive, it's upright. Okay? So is it inverted or is it upright? Very simple formula. And the magnitude tells you if it's shrinking or being enlarged. So if m is greater than 1, it's enlarged. However, if m is less than 1, it is shrunk. And what can you imagine m equals 0 is? Well, or m equals 1. Well, m equals 1 would mean that nothing happened. It was neither shrunk or enlarged. So we'll look at a practice problem or two using some of these formulas, but it's important just to kind of understand as we're going through, we can use these formulas. So we'll look at one more formula a little later, dealing with height when we get to that in these ray tracing diagrams. But this is our first one. It's a concave mirror when you're before the focal point. So a very important one to look at. But now let's assume a different scenario. Okay, let's say I take my friend here, my little arrow friend. I know that's a little weird to have arrow friends, but I do, I guess. And let's bring him in front of the focal point. So now he's beyond the focal point. Well, let's consider what happens. Well, let's draw a ray in the same fashion. A principal axis ray is gonna still go through the focal point. No matter where we are, that principal axis ray will always go through the focal point. So very important idea there. Okay, now let's consider what happens when we reflect about the middle, right? That's kind of like a plane mirror, we can think about it. It's gonna get reflected. But notice what's happening. Instead of seeming to want to converge to a point, they're diverging away from each other. So just to kind of show this, the distance here is small, but then the distance here is growing. Okay, so it's etching out a little cone, or I guess I should say a little wedge, and they're never gonna cross lines. Well, whenever you see this, remember I said you probably have a virtual image because they're gonna be converging behind the axes. Now, the way that we show this is we extrapolate backwards, and we're gonna see that the rays are converging right here, okay? So in this case, our image is on the other side. It's virtual too. And notice in this case, it seems to be enlarged. Now, you would need some numbers to crunch that up, but in this case, it looks like it is enlarged. All right, and it's upright too. Because notice, we would consider this distance, df, the image of our image. He's gonna be negative times a negative. That gives you a positive, right? D sub naught right here is in the positive direction of the mirror. That will give you a positive magnification. You're going to be upright. And notice because df is a lot larger than d naught in its magnitude, right? This is very close, a little bit further. You'll get an enlargement by m. Okay, so that about sums it up for concave mirror ray tracing. Those are the only two you need to know. If you're beyond the focal point, you get a little wedge of diverging rays. They converge behind the mirror. And if you're before that, you're going to get a inverted real image. Okay, we'll also talk about convex mirrors and their diagrams. So let's consider, we have the ground, we have our mirror, and let's put an observer, let's put him a little bits away. Let's say the focal point is here. Okay, the focal point, instead of being on the same side of our object, is actually on the other side. So let's draw some rays. Let's assume a ray goes straight on. Well, in this case, if you remember the principal axis rays, they're going to try to go through the focal point. In this case, it will go like that, extrapolating backwards, going through the focal point. Although I didn't really draw that very well, so let me redraw that. That's better. Okay. Now let's consider one that goes to the middle. Okay, that's just going to hit the center, and it's going to be reflected like a plane mirror, because if you think about the tangent here, the tangent plane to the surface, it's straight across or straight up and down. That governs law of reflection, and you'll get something like this. And notice when we extrapolate backwards, we get a very weird image. Now, when you are far away, you tend to get this, a shrunken virtual image. It's a very, very weird one, to say the least. I don't like this diagram. But notice your magnification, it just, look at the formula here for the magnification. We're going to see that df is small, do is large. The magnification says it's shrunk. And notice this is negative distance, this is positive distance, negative here, you're going to get a upright image. Okay, now that we have all that out of the way, kind of a fun one there. Let's now look at when we have a convex mirror, but we're really, really close to it. Okay, so maybe something like, say F is here, F is here. Okay, so we have this scenario. Let's imagine our guy has a principal axis ray emitted from him straight on. Well, it's going to try to go through the focal point. Although it seems I can't draw today, at least very well. I should have grabbed a ruler for this. Oh, that's not good either. Jeez. If only I could draw, guys. Do I have anything that could maybe help? No, that's not gonna help. Of course I had to draw the focal point like really far away. Okay, I think that will do. Yeah, that's fine. That's fine for me. That's the best you guys will get today. When we get really, really, really close to this mirror, let's see what's happening. This is a very, very crazy reflection angle. And when we extrapolate backwards, we're going to get the same thing. My point with doing this is no matter where you are in this convex mirror, it doesn't matter where you are, you're always going to get an upright image. It's always going to be virtual. So I just wanted to point that out to you guys. It's a very cool little phenomenon we get with these kind of mirrors. Okay, we'll do a couple problems now. I have a couple practice problems on my YouTube channel already, but we can do a few. Let's consider looking at some of this here. It won't work. Okay, well, I'll just make one up. That's fine. We're just going to do one really simple one. So let's consider so D naught is 15 centimeters. Your focal point is let's say 10 centimeters. Where is DF? Okay, your magnification, what is that? Upright or inverted? And then is it real or virtual? Okay, so answer these questions if you can, and let's see what you get. Okay, so let's draw a ray tracing diagram just to see what we're working with. We have a ray that comes like that through the focal point, and then this ray here, we just got to imagine might do something like this. So we're going to see that we're going to get a real image. It seems to be inverted, right? Because the rays are converging to a point, say right here, and the image is upside down. Okay, so we can actually go ahead and answer real or virtual. This is going to be a real image. It is inverted. But the things we can't really just look at and see is the distance final and the magnification. So let me go ahead and grab my calculator here. So 1 over d naught plus 1 over df equals 1 over f. This is how we're going to solve for df. We're going to plug in for d naught 15 centimeters, and f is 10. Okay, and then we can just do a little bit of rearranging. We can subtract 1 over 15. Okay, something like that. And then we can take the inverse. So in your calculator, you would do something like this. And this df now is going to come to the numerator. And let's see what happens when we get that. Okay, it turns out we get 30 centimeters. So our image is twice the distance from our object distance. So kind of an interesting thing here that we found. Nothing too crazy. But yeah, it's 30 centimeters away. Now let's consider the magnification. So what would that be? Well, magnification, like we said, is equal to negative df over d naught. So what we would do is we put a negative 30 over 15, and we know that to be, let me just draw that out quick, for 15 equals negative 2. So what does this tell you? Well, the 2 signifies that it is enlarged twice, so twice enlargement, but also keep in mind that with this specific image, because we have a negative sign, it's inverted, which we predicted with the ray tracing diagram. But yeah, in essence, that is mirrors. It's very simple. I tend to keep these lectures kind of light. We're not going to do another one, but I will give you a little warning about when you problem solve, and I'll give you one more formula you might see. So this regards focal points. So for a concave mirror, focal length is negative, or is positive, sorry. And vice versa for convex. For convex, focal length is negative. And how we really see this is, I'll just draw it quick. I don't want to spend too much time on this, but for a concave mirror, all the principal rays go through a focal point on the positive side, okay? All the principal rays go through that point, okay? But for a convex mirror, we said, okay, the principal rays, they appear to be going through the focal point, which is behind the mirror or in the negative side. So please, when you're problem solving, this side of the mirror is negative, this side is positive. I really hope that you can follow that because that is extremely critical in your understanding of, in problem solving, because like sure it's good to know all the theory, but if you don't know how to do the problems, it's really difficult. Okay, so just something I wanted to point out. And let's talk about one more formula and we'll get on to lenses. Okay, so the last formula that we're going to look at is this one, that HO over HI equals negative D naught over DI, or DF in this case. So I should change this to F2. So HO and HF are the heights. So if you're given a problem where you're given heights, use this formula. It basically relates, it's saying that, well, this would be 1 over magnification, but it's tricky, it all interplays. All it's doing is relating the distance of the image. So I have an object distance here, I have an image distance here, and it relates their heights. So they're proportional, and this is how so. Okay, so very, very simple formula. I don't want to go too much over it, but just know it exists, and if you're given a height and you're asked, okay, what's the image's final height, you now know. Okay, let's get on to lenses. Now I'm going to go ahead and erase all this, so if you need anything else, feel free, but it's all going away now. Alright guys, now let's talk about lenses, and before we do, we have to talk about refraction. Now, what Snell, a scientist, or physicist, I forget exactly his first or last name, but he made this law called Snell's law, and it describes this phenomenon that we see. Now, you'll probably get a little more of this when you talk about the wave model of light, but this is just something that they observed. So let's say we have a body of water. You've probably seen this phenomenon before. When the ray enters, hits the medium, right, some light ray, it has some incident angle, theta, let's say theta 1, okay? Here's the normal to that body of water. Well, what they found is with water, your diffracted ray, or theta 2, gets bent towards the normal, okay? Very important there. Theta 1, this incident ray comes in at some angle. Now when it enters the medium, it gets diffracted towards the normal. It's almost getting bent inwards, okay? And Snell saw this and made this idea of Snell's law. And it basically relates this thing called the index of refraction times sine of the theta of that angle to the index of refraction sine theta 2. So this is Snell's law, okay? Very, very, very important that we understand this, but to understand this, we need to know what this n value is. Now, when you enter a thicker medium as light, light slows down, and it's described by this value n, which is the index of refraction. Oh goodness, I was saying diffraction, refraction. So sorry about that. This phenomenon is refraction, because light is being refracted. There's diffraction, that's in the wave model of light. We won't talk about it here so much. But basically, it's describing this phenomenon that light slows down in thicker mediums. And to understand this, okay, we need to just know the formula. That n for any substance is equal to the speed of light in a vacuum, c, over the velocity in that space, okay? I'll give you a very simple example. The index of refraction for H2O is 1.33, okay? What is the speed that light travels through water? That's what this variable is. So let's solve for it. 1.33 equals c, which if you remember is 3.0 times 10 to the 8 meters per second. Okay, what's that final velocity? Well, it's going to be 3.0 times 10 to the 8 divided by 1.33. We're going to find that the velocity of light in water, or the speed of light in water, is we'll round that to 3 times 10 to the 8. So it slows down a little drastically compared to the magnificent 300 million meters per second, just to a slower 230 million meters a second. So that's the speed of light and how it changes on this idea of refraction. And it's a very important idea when we talk about lenses, because lenses are glass. Now the index of refraction of glass, let's say this is glass, this index would be 1.55 or around that. It's bending it pretty extremely because it's slowing it down so much. And there's a proof of Snell's law and this refraction idea, but that's, again, we'll see that in another chapter when we talk about the wave model of light. This is the ray model of light, a little different. Okay, so hopefully you got the idea of refraction. It's basically just saying once I enter a medium, my wave slows down dependent upon this diffraction. But now let's do a problem. I think it's very important. Let's assume now, because we're going to be talking about lenses, let's assume that this is a lens. So let's say the index of refraction of a lens is 1.55. Now, something important is in air, it's always 1. Okay, so in air, the index of refraction is always 1.0, and then once you go a couple decimals out, it changes. So it's very close to the speed of light. Very, 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 very close, but not quite. Okay, so let's say that we have here's our lens. Let's say we have an incident ray that's coming in at 50 degrees, and it's going from air to the lens. Okay, what's this output angle? Now all you need to do is just plug it into Snell's law. So N1 is, let's call N1 and theta 1 this angle here. So 1.0 times sine of 50 degrees is equal to 1.55 sine of theta 2. Now I want to make this abundantly clear to anyone who has not worked with trig functions a bit. How do you get that theta 2 out of there? I'll show you. It's not hard, but you need to remember this algebra. It's using inverse trigonometric functions. I'm going to get rid of the 1 because he's just 1, and quite frankly, I don't care. Well, when we solve for sine of theta 2, we're going to divide out the 1.55, and we're going to take the inverse sine, the arcsin, of both sides. So theta 2 solved for everything else looks like this. So let's see what theta 2 would be. So we find theta 2 to be roughly 29.6 degrees, okay? So it comes in at 50 degrees to this normal. Now it gets output at maybe about half of that. It gets curled in about 50% of the way and keeps going. Okay, very, very simple stuff. Before we get to lenses though, we need to talk about total internal reflection, okay? So let's take into consideration, let's say that this, instead of being air, was water, and now we go to a new medium, which is air. So we go from 1.33 to 1. I don't know, 0, right? As we've seen. Well, remember when we went from an index of refraction that was less than the index of refraction of the medium we were entering, we saw that it bent towards the normal. But notice now the index of refraction is higher in the entering medium than it is in the air. what this means is that instead of bending towards the normal, we're going to see that it actually begins to approach the surface. And there becomes a point where you start to approach this layer, and that's called total internal reflection. Basically, the maximum amount of reflection. Basically, you're basically just bordering this surface. Now, we can actually approach this and find what the critical angle would be to understand this. Now, assume that these index of refractions are correct, and imagine that we don't know some theta, which we're going to call the critical angle. Now, the critical angle is the angle such that we'll begin to see total internal reflection, okay? And the reason that that matters is because once you hit the critical angle, nothing's getting refracted, everything's getting reflected, basically. Total reflection, you can think about it as. Well, notice we want the ray then to travel this way, okay, along the border. Notice that gives you an angle of 90 degrees. So whenever you're asked to find total internal reflection, use this kind of setup. And I'll write a note down if you need it for your notes. I think that might be a little bit important. So total internal reflection is when theta 1, or sorry, not theta, when n1, the medium that you begin in, is greater than n2, there exists a critical angle that causes the refracted ray to bend 90 degrees to the normal. Okay, so that's the definition. When n1 is greater than n2, there exists a critical angle that causes the refracted ray to bend 90 degrees to the normal. So literally just bending 90 degrees. How we solve for this is Snell's law, right there. I hope we've seen this literally like a few seconds ago. Okay, so n1 sine of theta 1, where theta 1 is now theta c, which is the critical angle. That's what we're gonna call the critical angle. And remember, n2 is in this case air, or your refracted medium, and sine of 90 is a given. This is the point where we're gonna go from existing some sort of refraction to now 90 degrees, and you can't go beyond that. We'll find that once you exceed the critical angle, you're going to get so much refraction, the solution doesn't exist. It doesn't undergo refraction for those thetas. And we'll discuss that with the idea of the arcsin function, but we'll get to that. Okay, so how do we solve? Well, notice sine of 90 goes to 1, right? Because if you're at 90 degrees in the sine function, you're at 1, pretty obvious, on the unit circle, of course. So that means that theta c, right, if I divide out n1 and I take the arcsine, we get arcsine of n2 over n1. Okay, so it's pretty simple there. Basically, it says any theta that will give you 90 exists at some critical angle of c. Now, we can find this because we know what n1 and n2 are, n1 and n2. So we know that n1 is 1.33, or sorry, 1.33, and n2 is air, which is 1.0. Now, whatever is in here needs to be less than 1. I hope this is very important. You might get questions that will ask you, going from this medium to this one, where can you see total internal reflection? It has to be from a medium with a higher index of refraction to a lower index of refraction. And to understand this, you just need to know the arcsine function, and it looks something like this. and the domain is restricted, so the domain of all theta is an element of -1 to 1, okay? So basically that just means that the entire domain is between -1 and 1, okay, for all theta. Now if theta goes past 1, it doesn't exist. So for example, if I went from air to water, you wouldn't see total internal reflection, and that makes sense because if I go from air to water, it bends towards the normal. But if I go from a thicker medium to a lesser thick medium, we're going to see that it bends away from the normal. So please keep that in mind. That's the math way to show it, but there's the conceptual way too. So very important stuff here. Okay, now let's show what theta c will be and discuss that. My calculator, here it is. So the arcsin of 1.0/1.33, theta critical is going to be 48.7, okay? And basically what this means is anything past 48, so let's say this is 48.7, if I go a little bit past that, we're just going to get reflection. There's going to be 0 refraction that we're going to see. Anything less than 48.7 will get refracted. So let's say we have an angle like this, it might go something like that, okay? So an important concept, total internal reflection. And that's all you need to know about diffraction. Now I want to get into lenses. So this is kind of the application of refraction and is why, you know, you can see with your glasses, of course, and we might talk about that if time permits. We'll keep in mind Snell's law for some of these, so I won't erase that, but just like mirrors where you had convex, concave, you have convex and concave lenses. So a convex lens is known as a converging lens. Okay, you can also have a concave lens, which is known as a diverging lens. And these lenses, they use the law of refraction, Snell's law. And let's describe what's going on with these. So let's say we have some convex lens that looks something like this. And let's put an object, and let's say there's a focal distance right here. So let's say we're beyond the focal distance of a convex lens. So one more thing I want to point out before we continue is that 1/d0 plus 1/df equals 1/f. That formula still applies here, okay? So please know that this works, it exists. All your formulas work, your magnification, your height, your focal distance equals 2r, all exist. You even have focal points. And I guess we should start with that. If I have principal rays to this convex lens, it's going to all go through the focal point. This is why it's known as a converging lens, because all principal axis rays go through a centralized focal point. And an important distinction, other than that as converging, is the sign conventions, because they flip. It's so obnoxious and stupid, okay? F seems to be negative, but for a converging lens, F is always positive. Okay, F is always positive even though it's on the wrong side. But your image distance stays the same. So positive distance, negative distance, but F is always positive in this case. So please keep that in mind. Very, very critical point. Write that down in your notes if you have to. Okay, so as we had the converging lens, we also have concave or diverging lenses. And of course, my idiotic self had to draw a convex lens just now. And what this one looks like is, well, we have a focal point. Wow, this marker's so done. I'm just gonna put it in the corner there. He can cry about it later. We have some focal point here. All principal rays. This ray, of course, goes through like that. But when we have this one, it's going to diverge away. Sorry, I drew this one wrong. It goes like that. I'm switching up with mirrors. So this ray goes through. This ray goes like this, but then it approaches out such that it looks like it's going through the focal point. Words are really hard today if you can't tell. Same with this ray here. It will also do a similar sort of thing. And that's just the law of refraction. They all appear to go through this focal point here behind the mirror. And of course, in this case, because F was positive here, F is negative. So keep this convention in mind when you're doing your problem solving. F is positive for a convex lens, F is negative for a concave lens. And know what they're doing, right? This one's converging, this one's diverging, okay? All right, now let's discuss ray tracing diagrams for these because they can get a little tricky. Let's do convex lenses first. Let's consider before and after a focal point. Let's assume there's some F here, and we'll mark that that F is also existing over here. And let's put an image or a object, sorry, right here. When you have your principal axis ray, it converges to the focal point. And when we go, and here's an important point, I won't go ahead and prove this, but please prove this to yourself with the laws of refraction. When we go through the center, the normal is straight on, so it gets refracted, but then we can imagine it just going straight through, okay? When you have a ray that goes straight on, it just goes straight through that lens, unrefracted basically. It does undergo refraction, but it appears to go unrefracted. So please make sure you understand, and that's for thin lenses. It turns out it's not quite that simple, but it's so close we can ignore the refraction that comes out at the end. It's just straight to our eyes and to most of our instruments too that can measure this stuff. Okay, so let's consider where our image is. It's going to be right here, and we'll see we get a inverted image. Okay, so all your equations still hold. So if I give you a DO and an F, you could find DF here. Sorry, F and D naught. You could find DF. You could find magnification. You could find heights. You could find radius of curvature if you wanted. Uprightness or inversion. You can find all these things. Okay. And notice F in this case is positive even though it's on the negative side of the mirror. So keep that in mind. So in your problem solving, you would say 1 over D naught plus 1 over DF equals negative 1 over F, okay? And for all your problem solving, keeping in mind where your object is and where your final distance is. Okay, so that's if we are beyond the focal point. Let's now bring our guy closer, say, let's say he's right here, okay? Remember, principal axis rays still go through, so if I have one like this, it will still go through the focal point. But if I now go through the center, which will still give no refraction, notice that now we just have a big wedge, okay? So we have a wedge, and that means that the rays are diverging. Now when you see the wedge, for the love of God, just go behind it, extrapolate backwards. You're going to see it appears to be forming here. We're going to get a virtual upright image. and it will look like that, enlarged typically too. So if you're beyond the focal point, you're going to get a virtual image. So notice the switch. We got a real image because actual light rays converge. Here we get a virtual one. So that is convex lenses. Now let's talk about concave ones. Or I should say diverging lenses. So our formula goes back to normal. We have a positive focal length, even though it's the most stupid convention ever. It's just how the math works out, unfortunately. There's no intuitive way to really get that part, but... Okay, now let's consider some guy before the focal point. Okay, let's say we make a ray like this. It's going to bend, right, such that it goes through the focal point. And remember, a ray like this, okay, when he reaches the center, he just goes undiffracted. And notice where they end up, or they converge right here, because we would actually extrapolate backwards and we'll find that we get a virtual image. And the reason that this is virtual is because even though this line is real, it's going through and extrapolating backwards. That's why we're getting an image behind the mirror. Okay? Pretty simple there. I'm not going to talk about that much more and beat it to the ground, but it is virtual, so keep that in mind. Okay, now let's say we move beyond the focal point. Let's see if anything changes. So here's our focal point. Here's our nice little arrow guy. And let's say we have a ray that comes like this. Well, it's going to go probably more like that. And it's the same thing, as we'll see. We'll still see this kind of image form where it's just a smaller, closer version of itself. So these ones are really simple. You don't really get a whole lot with them. All right, guys, that's about it for this lecture. That covers all of lenses and mirrors. We're going to just do one more little topic that is just an application, and then we will be done. So this idea comes from, what if I have multiple of these components put together? Let's, for example, take two lenses, okay? Let's say we have something like this, and then we also put another convex lens. So what's going to happen? We have these series of lenses. Now, you'll see this in microscopes. We see this. We can see amplification of magnification, among other things too. Binoculars, they use lenses. A lot of things in life use lenses. And sometimes they use combinations. And we'll see some applications of this. So this, for example, might be what we see in a microscope, because we're going to see kind of a double inversion, as we'll see. So I'm going to speed through the ray diagrams. That wasn't very good, was it? Okay, let's say they converge here. We get an inverted image, a magnified real image, right? But it's inverted. And how we treat many lenses put together is we take that new image that we formed and we use it in our next lens. Very important topic there. That you must get. And it's very simple. Systematic treatment. treat this as its own system, and then use that generated output to then look at this system. It's a very engineering kind of way of thinking about things, breaking things down into its fundamental components. Okay, this one is going to be tricky. I got to do it backwards, it seems. Let's consider a different lens position. I don't like how this is shown. Maybe something like that. So let's say it hits the lens, and we have a focal point here. Well, we know it will go through like this, and let's say it goes through the center. Let's maybe make the focal point a little closer, just so you guys can actually see this. It might not show up. Maybe this is how you engineer it. You bring the focal point a little closer too. Okay, so something like this. Now, I didn't do this a whole lot of justice, granted. But when you put many lenses together, you can, if you want magnification and you want it to be upright, you put two lenses together because you can magnify it once. Now in reality, this would be magnified too. I just suck at drawing. But you would want your focal distance a little bit further out to really scale the image up. But yeah, basically what happens is we get inverted, we get magnified, and then we get inverted again and magnified even more. And that's the idea of lenses in succession, and you can get all sorts of weird phenomenon out of this. I don't know if you guys have ever been to a fun house before, like if you've ever been to Hershey Park, they have like the laugh track, you know, you're waiting in line, you see those mirrors, and it just makes you look all crazy. Same kind of concepts here, but we're talking about lenses, not mirrors. You can kind of make all sorts of wacky things, and in fact, like microscopes, for example, you have your objective and then your eyepiece magnification. Those are all lenses, and they give you some sort of magnification multiplied together. So yeah, very, very cool stuff here. That's all I have to say about that. I hope you guys enjoyed. Long lecture, I apologize, but yeah, hopefully you guys learned something. If you want some practice problems, be sure to check out my YouTube videos. I have all sorts of problems on there for you to look at. So with that said, have a wonderful day. Bye-bye.